we had some problems with the focus on the videos I did for this paper. Looks like the focus is now working. Hopefully it will stay. I think it's to do with the light intensity in the room. So we did, the last video kind of stopped abruptly on its own, so 18 wasn't finished. So I'm going to show you 18 and 19, the last two questions in the final YouTube video on this exam for Edexcel Physics International A-Level, Unit 2, Waves on Electricity, and the last two questions of the paper is what we're going to focus on. Okay, so I've already shown you question 18 in the previous video, so you can have a look at the explanation. So this is question 18, fiber optics, endoscopes. So an endoscope is a tool used in medicine. So a medical device can be used to see inside the digestive system or anywhere internally in the body. The endoscope contains bundles of very fine glass fibers. Here's one of them. Light is directed into the fiber, to illuminate the part of the digestive system being investigated. Light travels along the fibers by total internal reflection. So it goes in there. This angle is greater than the critical angle. It keeps bouncing off. So each of the subsequent reflections is that angle must be greater than the critical angle for glass and whatever is outside glass. I think in this case they're simplifying it to be air. Okay, so state the conditions required. It says for total internal reflection to occur. Well, the total internal reflection occurs when light travels into an optically denser material, so in this case the glass fiber, at an angle such that the angle of incidence internally, see diagram here, is greater than the critical angle for that material, or actually it's for the two materials because it's relative to each other. So here you got glass and outside we're assuming it's air. So that's your 2 marks. Second part, a ray of light is instant on the end of the glass fiber and refracts as it enters the glass. So here, see I've drawn the diagram again at the bottom to show you when it's entering at an angle. The one that they've drawn seems to be going in without deviation. Okay, so a ray of light enters the glass, so I've drawn it at an angle. So if this angle is at a specific number of degrees to the normal, then it's going to bend towards the normal. So a ray of light instant at the end of the glass fiber, and it refracts as it enters the glass. So then I want to talk about refraction. The first part was about total internal reflection. Okay, as glass is optically, so basically what's happening, they want to know, explain why light reflects as it enters the glass. This is like a GCSE level question in an A-level paper, but it's quality of your written communication that counts. Light slows down as it enters the glass from air. As glass is optically denser than air, higher refractive index. So I'm making sure I hit the nail on the head, and there's no doubt in the examiner's mind that I understand what I'm talking about. So you want to make sure you hit the message home so the examiner has the key words that he's looking for in your answer. And of course, we don't know what, when we're actually taking the exam, we don't know what's exactly in his mark scheme. So that's why I've put all this detail. So the angle of incidence on entry is greater, so this is the second marking point, is greater than the angle of refraction. So the angle in the air is greater than the angle of refraction as it bends towards the normal. So this is what's happening, and this is a GCSE style question, 2 more marks. So 4 marks entry into question 18, and then it gets complicated, and I'm sorry, I've overcomplicated the diagram with my arrows, which are my thinking arrows. That it says a diagram shows a ray of light, bending, being totally internally reflected. So here it is gone into the glass fiber and it's reflecting. Now, what I found confusing is that it's not to scale, and I didn't pay attention to this comment. So if you see it's not to scale, so don't get confused, because this angle, when we work it out, is 41.8, when it looks like it's greater than 45 degrees. So don't let that confuse you. If it's not to scale, they're deliberately seeing if your thinking skills are high enough. Okay, so at one side of the glass fiber, then refracting as it leaves here. So as it leaves, so it's entering here and it's leaving there. Here is air, here is water. So it enters through air and leaves in water. Okay, the angle of incidence at the boundary between the glass fiber and the air here is equal to the critical angle for the glass air interface. So I'm not sure why they're telling us that. And so much information can actually confuse people. So I think this is quite a confusing question for students. So it's coming in here, and they're telling us that we have to work out something. Determine the angle theta. So I put that as theta 2, as it between the emerging ray and the normal. So the emerging ray is this one, yeah. So this is the emerging ray, and the normal. Well, the normal is a dotted line, as you should know. So they've given us all the refractive indices: water 1.3, glass 1.5, and air 1.00, to 3 significant figures. So the light reflects and then refracts. Okay, so they've already checked whether you understand what total internal reflection means here, and what refraction means in your answer. So determine the angle, and it tells us here the angle of incidence at the boundary between the glass fiber and air is equal to the critical angle for the glass air interface. So if we know that, yeah, we can find out what the critical angle is. And they're telling us that that's equal to this angle. That's all it is. So it's just to make sure you've understood that this angle is equal to the critical angle. And we know from the equations given to us that sine of the critical angle is 1 over the refractive index. And this case is for glass and air. For glass and air is 1.5 to 1.00. So that's what you've got to do. I can't talk now. So when you do that, the angle is 41.8 degrees. And when you then, once you've got that angle, you can then work out what is theta 1. Okay? Sorry, I just got interrupted by someone coming in the room. So if this is 41.8 degrees, you can use your ability to do right angle triangles or alternate angles. So you can work out this is a right angle triangle there, then the theta 1 is going to be 90 minus 41.8 degrees, which is 48.2 degrees. So once you've got that, you know this is 48.2 degrees. Then you use the equation here, which is given to you in the back of your exam. Yeah, and this time is for glass and water. So we know theta 1, so that's why I changed theta to theta 2. They want us to work out theta here. So this is theta 1, this is theta 2. So once you do that, you know that N1 is for this material, theta 1 is for this material, which is glass. The second material is where it's going into, which is water. So this is N2, yeah, and this is theta 2. So once you do that, we know N1, we know sine theta 1, and we know N2, we don't know sine theta 2. You do the mathematics, and you'll see that sine theta 2 will be 0.86. You don't get a mark for that. You've got to, oh, I'm sorry, my maths is not showing. So you're using, sorry, I have to go back and show you that this is a similar, from the right angle triangles, you can work out theta 1. You use the equation from the back given to you, N1 sine theta 1 is N1 here, 1.5, theta 1 in the first medium, and when it's exiting, theta 2 is for water. We know N2, we don't know theta 2. So we know this, we know this, we know this, we don't know sine theta 2 for the glass water situation. You put the numbers in the equations, inserting your numbers, you'll get 1 mark for that, presumably, and then you'll get, so I think there's 1 mark for doing this, yeah, which is my green tick hidden underneath the black writing. So 1, 2, 3, all you've got to do is then solve for it, and you'll get 59.3 degrees. So you can keep it to 3 significant figures, or to 2 significant figures should be sufficient as well. So I've done it for both. And you can do that in the exam to hedge your bets as to what the examiner's looking for. But since we worked out the critical angle was 41.8 and we did 48.2, then there's no reason why you can't stay to 3 significant figures for question 18. So that's the summary of what we did in question 18. And then question 19 is the final exam question, and so far the autofocus is working okay. I'll just give you 1 second to read the question. I'm just going to turn the AC up. It says a student carry out an experiment to determine the EMF of the internal resistance of a potato cell. So basically a potato battery. I use these with my year 7 students as well as my year 9 students to make sure they understand that a battery is basically a chemical process between two different electrodes. The potato used in this experiment was connected to the rest of the circuit using the two metals as shown. So two different metals there creates a voltage across them, and that's what an EMF is. So the electromotive force. Complete the diagram below to show a circuit that could be used in order to determine E, which is the EMF, and R, which is the internal resistance, yeah, inside this potato, in this case what we're using for our cell. It's 2 marks. So obviously you need to have a voltmeter to measure the potential difference across the cell as you change the current that's being drawn from it. As you increase the current being drawn from it, yeah, then the voltage will drop across it, and that's the theory behind internal resistance, how you work it out. So once you've got this circuit, you need to have the voltmeter across the potato cell, and you want to see how does the voltage drop when you change the current. So obviously you need to have a way of changing the current. The easiest one for this syllabus, they seem to like this, is just to have a variable resistor. You vary the resistance. The voltage is trying to be maintained at the EMF, but it can't. As you draw current through it, the current goes through the external resistance, but also goes through the EMF internal resistance. So it also goes in there. So obviously if the current is I, some of the current heats up the internal resistance of the potato cell, and you lose some voltage in there. Okay, so the EMF will become equal to I external resistance, so they say that's the external resistance, plus I times the internal resistance, and this amount is called the lost volts. Okay, that's the theory behind it. So you get 2 marks for getting all the components of the circuit, and you can check the syllabus, the mark scheme, to see exactly what they're giving the mark for. I think they're giving you a mark for making sure the voltage and the ammeter are in the right place, and obviously a way of changing it. You have a variable resistor to vary the current. Okay, so that's how you then measure the terminal potential difference, and that's going to vary as the current varies. So change the resistance, measure the current and the terminal potential difference, and then you plot a graph. In part B, they've given you the graph, and they want you to draw the line of best fit. The student completed the experiment, plotted a graph showing the relationship between the potential difference V, yes, that's the terminal potential difference, and the current that was being drawn through the external resistance, which could be varied. So they've gone 1, 2, 3, 4, 5, 6, 7, 8, 9 data points in the graph. Some of the data points are above the line, some of them below the line, as I've drawn it. And then basically the EMF is the maximum voltage, where the current is 0 is the EMF, where you haven't lost any of the voltage. So you can find the intercept on the y-axis is equal to the EMF, and the gradient, yeah, voltage against current is gradient. So because remember, resistance is equal to the lost volts, so how much EMF to say to here, that's where I've done it to, the final reading, is the lost volts, the change in the voltage from the 0 current to the point on the graph that you want to use your gradient, divided by the current, yeah? So the current here, you can see is 0.44 milliamps, and the current when the EMF was maximum is there. So you've got to work out that the change in current went from 0.44 to there. Show it on the graph. It's a good way of doing it. And here is 0.285. I make that the maximum voltage, so it's 0.275 because I've chosen the value at 0.10 to make it easy to do the graph. Okay, so draw the line of best fit, 1 mark, intercept on the y-axis to 2 significant figures, 0.285 can be rounded up, so you get a mark for that. And then for the gradient, show it clearly on your graph. It will give you a value of negative, because the gradient is going down, minus 185, yes, 0.1, sorry, I've done it the wrong way around. We should have done it the other way around. 275. So it's 0.10. So I've done this wrong. Over here, it's right. So this is the top bit. It's 0.10 at the final bit, so final minus initial, 0.10 minus 0.285. So you could say that's there is minus 0.185 divided by the change in current, which we looked at above. From there, the change in current is there, 0.44 milliamps. So that's milliamps. So it's times 10 to the minus 3. It gives you a steepness, a negative steepness of 420. The units of voltage against current is obviously ohms. So you get two significant figures. So you get, I think you get a mark for doing the calculations correctly. So I haven't actually put where the fourth mark is. I don't know if it's here or elsewhere. Let me see if I've got the mark scheme to hand. So line of best fit, 1 mark. Working out the EMF, 1 mark. Working out the size of the gradient, the magnitude of the gradient, and it has to be roughly between 400 and 430. I've got 420, so I get that mark. And then quoting the resistance, so 1 mark for there. There's your fourth mark. Okay, so this is a very common question in this syllabus, is knowing that the EMF is always the intercept on the y-axis, and R is the gradient, which is negative on the voltage terminal potential difference against the current, will give you the internal resistance. Hope that makes sense. Now there is a final part, which is part C. It says in a separate experiment, 2 resistors are with equal resistances are connected to a battery. It's actually a cell with internal resistance. So there is some internal resistance here as well. So you can say there is internal resistance in the cell there. With the 2 resistors fully in a series arrangement here, diagram A, and then in a parallel arrangement, diagram B. Now you know if you just add 2 resistors in series, the total resistance is twice the individual resistances. But in parallel, the resistance drops, because in parallel the equation is 1 over RT equals 1 over R1 plus 1 over R2. Yes, so it'll be 2 over R, so the resistance will go down. And if they're identical, it will be half the resistance. So this resistance is less, and this resistance series is higher. So if the resistance is higher, the current here will be lower, and the current here will be higher. Okay, so IB, the current in circuit B, will be greater than the current in circuit A. If that happens, the current here will also be higher, so there is more lost volts in this cell than there will be in this cell where the current is smaller. So in circuit A, you've got to say series, the resistance is greater than circuit B, so current in circuit A will be less than in the parallel circuit. So less voltage will be lost in the internal resistance of the battery. Okay, they've actually used a cell rather than a battery symbol, so they seem to use the terms interchangeably, which is technically incorrect. So the terminal potential difference will be greater in circuit A. Yeah, so here if you had a voltmeter across there, the voltage in A would be greater than the voltage in B. Okay, for the arrangements shown. Hope that makes sense. Well, that finally brings us to the end of this paper. It's been a little bit of a problem with the technical issues. I now know that it's due to the light intensity level, and seems to be, once it's lost its autofocus ability, then it's difficult to bring it back. So I had to restart everything and then make sure that we're in a well-lit room. Okay, so this is the end of the May 2019 paper. Yeah, so I hope you found that useful. If you did, please give us a like. We are trying to provide this service for everyone. So this is question 18 to 19, and that's the final YouTube. We're trying to make this service available for anyone taking these exams. I'm also expanding this year into doing later on in the year some of the linear Edexcel exams. Please share the exam with your friends who are taking the same paper. If you're retaking in October, the exam is soon, and that's why I'm focusing on Unit 2, because some students who took it in June, who I teach, need to improve their grades for the university they're going to. So please like and share just to show your support, and also subscribe so you'll see when the next video is being produced. I do as many as I can, but I'm also working full time. So thanks for watching, and hopefully see you in the next video. Bye for now.